today we're going to walk through our Lab 14 GAN. So before we dive into the code, let me quickly review what a GAN is. So GAN stands for Generative Adversarial Network, and it consists of two neural networks that are trained together in a competitive setup. So we have a generator and a discriminator. Let's take a look at this image. The generator takes random noise as input and tries to produce realistic looking data. In our case, it'll be the human face images. While the discriminator's job is the opposite. It looks at an image and tries to decide whether it's real, meaning it came from the real image dataset, or is it fake, meaning it was produced by the generator. So during this training, these two networks plays what's basically a minimax game against each other. The generator improves by learning how to fool the discriminator, while the discriminator improves by becoming better at detecting the generator's fake samples. So as this process continues, the generator gradually becomes better and better at creating outputs that look like real data. And GANs have been used for all kinds of generative tasks, not just images, but also music, text, and even 3D shapes. So if you want to look at the original paper, it's by Len Goodfellow in 2014, and it's the reference is here. And for today's lab, we're going to implement a DC GAN. That's a GAN architecture that specifically uses deep convolutional layers in both the generator and discriminator. And our goal is to train this DC GAN on the Celeb A dataset. And finally, we're going to generate realistic 64 by 64 human face images. So here, let's come to the code. These are just dependencies that you need to import. Here, you also need to download the dataset from this link and then do the following steps. Put it in your Google Colab, Google Drive, yeah. And then you're gonna run through this code to unzip it and extract the dataset. So here's the hyperparameter setting. You need to set the data root to exactly the same as here, and you can also specify the number of workers for data loader and batch size for training and image size of training images. So right here we're going to use 64 by 64, and NC is the number of channels. So for our training images, because it's RGB images, so the number of channels is 3. And we're gonna specify a size of Z latent vector. So right now we can set it as 100, and also specify the size of feature maps in generator and size of feature maps in discriminator. And we're gonna train 5 epochs, and learning rate is 0.0002, and we're also gonna set up the hyperparameter for atom optimizer. Okay, and here's the data loader. You can implement some data transformation here, like resize, center crop, and normalize. Yeah. So you can take a look at our training images here. And then we're also going to do weight initialization. So here it comes to our very important part, which is generator. We're going to define the class of generator code. So basically, the generator network used transposed convolutions to upsample from a latent vector to a 64 by 64 image. So in our generator class, this is just basically the number of GPUs that we specified in our hyperparameters configuration, and here, this whole block is a sequential container that holds the actual layers of the generator. The first layer is a transpose convolutional layer that expands the noise factor Z into a 4x4 feature map. So right now we can see this is the input channel, and this is the output feature dimension. And this indicates the kernel size. This indicates the stride, and this indicates the padding. So after this, we're also going to implement the batch norm and ReLU. Convolutional transpose and batch norm to ReLU is the standard DC GAN building block and helps with stable training. And after this, we get an image size that's 4x4, but the channel is number of features in generator multiplied by 8. Okay, and we have the exact same block again, but with different dimension of features, and our output became like this. So this is the number of channels, and this is the image size. And after several times, we come to our last block. So finally, we upsample one more time to reach 64 by 64 and drop the channels down to the number of channels, which we specified in our configuration. So it equals to 3 because this is our RGB image. And finally, we're going to use this activation function at the end. So the pixel values are in the range of -1 to 1. So it'll match the normalization we applied to the training images. So after we define the generator code, we're going to instantiate the generator. So in this part, it's just basically create the generator model and moves it to the correct device. And we come here. If we have more than one GPU available, we're going to wrap the model in n.data parallel. So that could let PyTorch automatically split the batch across multiple GPUs for us. And here we apply a custom weights initiation function to every layer in the generator, and this function is defined earlier in the notebook. So it's here. So what this does is it sets all convolution and batch norm weights with a normal distribution, whose mean is 0 and standard deviation is 0.02. So this is also the recommended initialization in the DC GAN paper. And finally, we can print the model, the generator model. We can see, so this column is the image size, and this column is the dimension of features, and we can also see the whole architecture of this model. And after the generator, we come to the discriminator. So basically, the discriminator is basically the reverse of the generator. Okay, so let's also take a look at the sequential container. For the first convolutional layer, it goes from an RGB image with so this number of channel for RGB image is 3, and its channel is gonna come to 64, which we specified before. So NDF is the number of features in discriminator. Okay, and this is the kernel size, and this is the stride, this is the padding. Okay, so right now we use leaky ReLU instead of ReLU because we want to avoid dead gradients on the negative side. And after several blocks, we goes to the final block here. So the last convolutional layer is like a fully connected layer implemented as a 4x4 convolution. It collapses the 4x4 multiplied by NDF multiplied by 8 feature map down to a single scalar per image. Then we apply a sigmoid to turn that scalar into a probability between 0 and 1, representing the realness, which is the output of the discriminator. And next, we're going to instantiate the discriminator, which is similar to the instantiation of generator. And now we come to the loss function and optimizer. So here in GAN, we're going to use binary cross entropy loss. because the discriminator is a binary classifier. It identifies real or fake. And the same loss is also used indirectly when training the generator, since the generator is trying to make the discriminator output real for its fake images. And we're going to establish the convention for real and fake labels during training. These are just convenient constants. When we show a real image to the discriminator, we use label 1. Then we show a fake image, we use label 0. And we're going to set up the optimizer. So both of the discriminator and generator optimizer, we're going to use atom optimizer. And here's the learning rate and betas. Okay, so after we set up all the things that we need when we are training this, here we comes to our training process. So this training loop is the core of how our DC GAN learns. The structure follows the original GAN paper. So in every iteration, we're going to train the discriminator with real and fake images first to update the parameter, to update the weights of discriminator. And then after that, within the same iteration, we're going to train the generator as well to fool the discriminator. And we're also going to log losses and save generated images periodically. So let's take a look at the code. First, we need to initialize these lists to store generated images and the generator loss and the discriminator loss and also the iteration. And then we're going to start the loop. So we're going to first iterate over epochs. And inside each epoch, we're going to iterate over batches from the data loader. So each batch contains a set of real images from slab A. And let's come here. So the first thing that we need to do is to train the discriminator network using the real and fake image. So first we're going to train with all real batch. So here we first clear old gradients for the discriminator, and then we load the real image from the batch and assign them to the label 1, meaning real. And then we run the real batch through discriminator, and we compute the binary cross entropy loss against the real label and backpropagate. So right now, the dx is a diagnostic value showing how confidently D, which is discriminator, recognizes real images. And when we are training discriminator, we still need to train with all fake batch. And how do we have the fake samples, fake images? We're going to use generator to generate fake image first, and then put those image in the discriminator. So when we are using the generator, we label them as 0, meaning they're fake, and then we feed them in discriminator, and then we compute discriminator's loss on fake data and propagate again. So we're going to detach the fake images so that the gradients don't flow into generator doing discriminator's update. And finally we're going to get DGZ1. It tells us how confidently D classifies these fake samples as fake. And then we're going to update this era of discriminator. Okay, and after we train and update the discriminator's weights, we're going to update the generator's network. So for a generator, we first also clear old gradients, and we compute the generator's gradients and update its parameters here. So we get DGZ2. It measures how well the generator fooled the discriminator after this update. And the following parts are something about logging and visualization. So this basically means every 50 batches we print out useful debugging and information. And we're going to save the losses and save generated sample every 500 epochs. So here's the log of the training process. And then here we comes to our results. So from this visualization, we can see that the loss of generator is constantly decreasing, which means the generator is starting to generate more and more real images that cannot be identified as fake by the discriminator. And then we can also visualize the generator's progression. So we comes to the first one, first epoch. It's complete noise, and then after several steps we can see that we can generate some blurry images, and it got more clear, and we can see some of the faces. Yeah, it's just getting better and better. Yeah. And finally, we can also use this code to compare the real images and our generated fake images. You can see it's not bad right now. Okay. That's all for today's Scan Lab.